Hello and welcome to Advanced Topics in MATLAB. This presentation will be by James Bittner and it's being put together for the Civil Engineering program at the University of Illinois, specifically Wave Propagation, CEE 598 WP for fall 2014. So this presentation will cover three topics in Advanced Topics in MATLAB. The three topics will be data types, such as cells and structs, speed optimization, which is typically a common problem with engineering code, and GUI generation. I myself profess to be only an engineer and just a practitioner in all of these topics. I'll present all of the neat tricks and interesting observations that I've made in putting my code together. Hopefully it'll save all of the people watching time in generating their code, and we'll go through a tutorial in class as part of the flipped class style. So basically this class is being offered as a flipped class style. We'll watch short 6 to 8 minute videos online per topic, so 3 videos. And then in class we will do a tutorial, and that will be turned in as the homework. So instead of doing the passive watching and just listening, we'll do that online, and then we'll do the homework in a classroom setting. The first item we'll talk about is advanced data types. The first advanced data type we'll talk about is cell. I'm sure everybody's already familiar with vectors. Being defined here, A equals just the vector of numerically 5, 4, 3, 2, 1, just some integers. The way that MATLAB handles those is it allocates a certain amount of memory ahead of time. Since it knows there will be 5 items, it allocates 5 chunks of memory for integers. This starts to be a problem when you work with more complicated data sets, and your data sets start to include strings mixed in with other variables and other complex values for each of your rows in your array. MATLAB came up with a solution for this, and they use the word cells. It allows many different data types for each item. So we can define it here with curly brackets, and we can define an integer, and then a string, and then an integer. So when you're building tables together and you're iterating over a certain number of calculations, you can form these rough arrays, which are of mixed data types. The way MATLAB handles these is it makes almost a separate variable internally and then defines that to a memory location. So it can change this memory size without affecting any of the other variables in the cell array. And you can see how it could do that if it just labeled x1 for the first item, x2 for the second item, and then as define those separate variables as an integer or as a string. So the pros and cons to think about when you're looking at cell arrays is that they're very fast to write, and they're great for testing code. On the negative side, they tend to have limited organization. You're still limited to rows and columns. And for large data arrays, they can be slow because it's keeping track of almost 2 arrays. It's keeping track of an array of where to look for each one of these items. So moving on to deal with the limited organization, we'll first start out with structs. Structures are great because they provide a structure to data groupings, much like a tree, but upside down. So if we look at an upside down picture of a tree here, we can see the roots coming up into the top. So there's one main trunk here, and then down the branches, and then out to each of the individual leaves on the end. And each of the leaves would be a data item. And you can have data items come off at any point along the tree. So if we put this into a data perspective, we'll just slide up here. If we put this into a data perspective, for example, a testing sample, we can see that a sample has a geometric properties, and then it maybe has a load displacement curve. And the geometric properties are integer items, such as height, width, and length, whereas the testing properties, such as a load displacement curve, can be a vector of observations during a time series. So fundamentally, why do we use structs? 70% of the use of structs is for easy code writing. This is a benefit to you. 30% of structs, in my opinion, is for easy code reading, the next guy. Oftentimes we can write super complicated code and it would be impossible for anybody to read it. For example, here's a easy to write line of code, plot, from our sample struct up here. We'll sample.ld.load by sample.ld.displacement. And as a benefit for the next gentleman reading your code, it's easy to read. So those are really the benefits of structs, and now we'll demonstrate struct generation and use in MATLAB.
Okay, now we'll do a quick demonstration in MATLAB. First, we have here for advanced data types, you can see that we are generating a vector, as we're all very familiar with. Now if we try to generate a vector with a complex data set, it has a string in there. First we'll generate A, and we can see that it was nicely generated with 1, 3, and 5 as the items. Now when we try to generate the same with a complex with a string instead of a numerical on the second item, you can see that it fixes A to be just the string. It ignores the items 1 and 5. We can get around this by using cells, which will allow us to have a complex vector. And you can see that it saves the first item as its own vector. It saves the string cookie as a second vector, and the final item 5 as a vector. So to identify these, you can address the contents of the cell or the contents of the array by using the squirrely brackets or the rounded brackets. And so we'll do both of those here, and you can see the results. So A with the curly brackets gives you the numerical result 1, and A with the rounded brackets returns the vector in the first array or vector location. So you can see that a cell is just a cell, as we defined as A, is just a vector of vectors. And so this is a vector of length 1 inside the vector at location 1, and this is a vector of length cookie inside the vector at location 2, and this is a vector of length 1 of the numerical 5 at item 3. So moving on to structs, we'll clear the screen here. For structs, we'll define a struct as a structured data set, and we'll do our grouping. For example, if you're doing a load displacement test on a concrete cylinder, and so we'll define a unit test as a blank struct right here. And then we'll define a name for our cylinder, such as cylinder 5, and we'll define a substructure of dimensions, and we'll label those X, Y, and Z, and we'll do those in millimeters, and we'll put in a weight, and we'll put in two vectors, a load vector and a displacement vector. And so we can see what this looks like. Right here, we'll run it, and if we type unit test, it'll display us what is valid inside that struct, and you can see we have a name, cylinder 5, dimension is a substructure, weight is 2.5, load and displacement vectors are plotted right there. And so now if we wanted to have multiple unit tests or multiple test cylinders, we can create, very simply, we just make an array and we make the first item in that array our structure from before. And so right here we're going to make an array of 2, and we're just going to copy that unit test in twice, and on the second item we're going to change that unit test name to cylinder 6. And so we'll run this code right here. And there we go. When we type test data tells us that we have an array of structures with the fields name, dimension, weight, load, and displacement. And so now if we were interested in the dimensions, we can type test data 1 dot dimension, and it'll show us for the first cylinder what the dimensions are. So the real value of this comes when you go to work with large test data sets and you have maybe 1,000 cylinders worth of data. You can plot 1, 2, or up to 1,000 with just a couple lines of code here. So right here we can see that we have a for loop running for the length of test data, so as many unit test information we have in here as an array called test data. We'll generate a figure, we'll plot the test data of that item of test data, we'll plot the load versus the displacement, and then we'll put simple labels on there, and we'll run this code. So run section. And as you can see here, we've generated just 2 plots, but each plot has proper labeling and a title defined by which number it is in the array. So this makes it very easy for people to come in and read your code and understand what's going on without having pages and pages of multiple variable names.
Okay, moving on to optimization. Here we're going to talk about how to optimize your code to make it run faster and be able to generate more results quickly, which is a great debate. Optimization is a huge field in computer science, and many people are working on it. So oftentimes, being an engineer, trying to decode the technical speak of a whole nother field is often difficult. From my calculations and experiences, it all comes down to this basic plot. Basically, the time to write your code versus the time to run your code. And ultimately, when you start out a project, you start down here. You haven't really spent much time writing the code, and it takes quite a while to run the code, so it's very unoptimized. As you spend more time rerunning your code or getting told to run it with different variables, you end up moving in a probably not linear fashion, but in a obscure fashion up towards lower run to time the code, but lower time to run the code, but increased time to write the code. And this is the balance between optimization. How long should you spend writing the code versus how many times do you have to run the code over your entire lifespan? Some factors that affect it are the complexity of the code. If you're trying to do a huge finite element simulation, or if you're just trying to read in an impact echo single reading, or in the size of the platform doing the calculation. If you're running on a large cloud system for high availability, you're going to have to optimize your code because it'll be run on multiple different platforms many different times. So basically it comes down to the field of what languages are available. We start out with a high-level language, and this is what most engineers are familiar with, MATLAB or Python or Perl. Their computation per line of code is quite slow, but their construction, the time to write the code, is extremely fast. This allows very easy optimization in terms of trying to get the right data input into the question. As we move to mid-level programming languages such as C or Java, their computation time is faster per line, but their construction time is considerably slower, and you end up almost having to have an entirely professional coder in order to work in the mid-level range. And for the low-level range, you're talking machine code or even transistor-based. And these are often extremely senior electrical engineers writing these codes, but the computation is the fastest available. Unfortunately, the construction is the longest. Typically, you could spend a career learning all of the low-level languages for a single chip. So the trick to optimizing your code in MATLAB is that MATLAB's functions are mostly written in lower-level languages than MATLAB. So you should put all your loops, your calculations, and your search functions in internal functions. So if the trick is to put loops, calculations, and search functions in internal functions, how can you find the code that is slow and you need to optimize that code? We can't go and optimize every line of code because that would take too long and would push us way too far on time to write the code. So there's two very simple ways in which MATLAB provides you to optimize and find slow code. The first simple one is tick-tock. And tick-tock shows the elapsed time for a function to run, and you can write it just as tick, and then you write your code. This can be multiple lines or even a function call, and then tock. And when the computer comes across these two numbers, it'll calculate the time difference and spit it out as the elapsed time. The more in-depth method of finding slow lines of code is the profiler demo. The profiler will run your code and keep track of every line and how many times it's executed and how long each line takes. Then at the end of running your code, it'll give you a graphical observation over how long each line took and how many times it was run. And it'll show you that for your entire code that you input. And you can even dive down with Profiler inside functions that are run by your code. Once the slow code is found and identified in specific lines of your code, to optimize that code or to find faster ways of running it, the order of optimization or the tricks that I would use would be first, try to solve the problem with matrix math. If you could remove multiple for loops by putting all of the values into matrices and having the matrices do the multiplication or solving for specific variables, that's typically the fastest method to go about optimization. Next, another great alternative after you've tried to use matrix math is to use internal functions. Oftentimes the internal functions in MATLAB, computer scientists have spent many hours trying to implement matrix math solutions or tricks in order to solve for, and you'll find incredible speed available using internal functions. And lastly, as your last option, I would suggest going for the parallel processing. MATLAB has an excellent parallel processing toolkit. Unfortunately, you deal with all of the issues with parallel processing, such as transferring your data and potential excessive costs of having to buy multiple processing units. Okay, on to the demonstration.
The first step in optimization will be identifying areas of your code that's very slow to run. Oftentimes we have a complicated long set of code This, for example, is a simple finite element calculation. We have a rod and a heater placed at 0.4 meters along the rod and 0 boundary conditions placed on either end of the rod. And as you can see, we try to resolve the temperature along the rod from this heat source. And so basically we have our stiffness matrix being generated, we have our force vector being generated, and then we run the system of equations and solve for the unknowns, and then we plot these. So quite a few things being taking place here. So we'll run and time up here. This is different than the run command, but we'll run in time, and then MATLAB will run this section of code, and it'll run a profiler at the same time. And here's our plot that comes up, so I'll close that. And right here it provides a listing of function names along with the total time spent in each function. And you can see a nice graphical representation here. So we're most interested in the finite element. So FEA, we'll enter this. And then here is the results of our code. So the lines where the most time was spent was some wrapping up calls, some end calls. And then right here you can see that there's just a simple if check, and then assigning a variable, so there must be a lot of zeros. This function was called approximately 158,000 times for a total time of 0.5 seconds for the ends, 0.461 for this one, and it'll show you the percentage of times. So ultimately this is very efficient code because it's no one function call or one calculation is taking up the most amount of time. One of the great things about this profiler is down here it'll actually highlight your code, and it'll highlight in red lines that are computationally intensive or the ones that are taking the longest amount of time. And as most people know in finite element solutions, the stiffness matrix is a pretty large matrix, and generating the stiffness matrix requires quite a bit of looping with logic flow. And as you can see here, that's where the most amount of time and number of calls are being had. Our actual calculation, we're solving the system of equations, is pretty trivial compared to the time to build up all of the matrices. And lastly, the plot command is another large expensive function. So if we were to go optimize this code, we could look into optimizing how we generate this stiffness matrix. Perhaps if we could generate one matrix and then expand it out using a localized reference rather than using a global stiffness matrix. Okay, moving forward, once we have our section of code, how do we optimize it? And so right here we have an example of using for loops to generate a simple distance calculation. So we're calculating the row squared plus the column squared, and then we're taking the square root of that. So we're basically calculating the distance from the origin for a matrix of 1,000 by 1,000. And so for loops, we can do that simply using this. We'll time it with the tick and the tock commands to calculate the time elapsed. We'll run this section. And so the total time taken for using for loops was 0.8 seconds. If we then use to parallel optimization, so as you can see here, we've put in the par4 command, and so that's going to parallelize this loop out to all of the different processors. And then since each I is separate, none of the distance matrix is being shared with any other section of the solution. And so we'll run that. And that actually has taken 1.2 seconds. So actually parallelizing this command, due to the communication of having to spawn off the process and then spawn off all of the memory, ends up taking longer for doing just this simple for loop. And so the best solution we can do is come up with a matrix solution. So right here we generate a vector and we square the individual items in that vector, and then we add that to the same exact thing calculated for the other dimension. And then we take the square root of that entire matrix solution, and the square root function in this case will operate item by item across all of the 1 million entries. And we'll run this section here, and that takes the least amount of time. So right here you can see that here we have the for loop, here we have the parallel for loop, and here we have the matrix solution. And the matrix solution is significantly quicker than all of the other options. Real quick, one of the features of MATLAB that is really not well talked about or worked with is the publishing feature. So up in our editor, we're used to seeing the run the time. There's another button up here called publish, and in publish you can, you're given a bunch of editing options, such as selecting an output folder. So we'll just use the default here of outputting to a PDF. It also gives you options to output to HTML, LaTeX, or if you're on Windows, you can output directly to Word. and we'll click Publish. And MATLAB will run your code and put all of the figures and everything into a PDF for you. And based on your commenting of the code, it'll generate these headers, and it'll show you the code that's actually running, all colored, and then it'll show the output of the code for each of the sections. So you can do a header, you can provide some sort of comment in your subheader, and you'll run your code, and then based on the results of that code, you can provide a little comment. And how that looks in the MATLAB file is you just put 2 percentage signs for the header, 1 percentage sign for the subheader, and then you run your code just as you would normally. And then for your next section of code, you just start out with 2 percentage signs, and this breaks up your chunks. To add a comment at the end, you do 2 percentage signs with nothing after it, and then single percentage signs, and this will show up as text. As we have here, the text will show up right here in just normal Times New Roman. So this also works with plots, and it's a great way of keeping your code all cleaned up.
Moving on to our final topic of this brief web video, we'll be talking about graphical user interfaces, or GUIs. The wonderful toolbox provided by MATLAB is called Guide for generating GUIs. But first we'll talk about what generally is a GUI. Oftentimes, most of our interactions with computers are through GUIs, but we don't have a good concept of what is driving the GUI and how much work it takes to generate a GUI. So the first example in which most of our MATLAB scripts run is in the command line driven event. So for an example, we would run the command start.m. It would run some input functions and ask us for data or pull from files. It would run our calculation section of the code. And then ultimately we would want it to output a plot, some table, or maybe even output an output file to be opened by an external program or an image viewer. And then the program's done. It returns it back to the command line and we can run another program. However, in the GUI world, in the graphical user interface world, the code is never done. So basically, in a GUI-driven environment, we have a setup that creates a window and then waits for user input. Upon the user clicking a button or loading some data, it processes the input, runs the calc, takes the output, and then updates the window. And so this window gets repopulated with new values. And then it enters back into this wait loop. And you can see that the loop continually runs as if we click another button or cause another event to happen. This continually monitoring for observations happens across all windows on your computer. And you can see how over time, until the program is killed, this starts to become very CPU intensive based on the response time. If you want to be able to click a button and see the effect right away, the computer program needs to be monitoring for your input constantly. Modern computer programs have offloaded all of this to the operating system in order to monitor for quick response. But ultimately, if someone clicks a button 1,000 times, the program will update 1,000 times. So moving forward, the guide toolbox in MATLAB generates a window figure. In Guide, you're able to click buttons and drag features for your window, such as a plot box or command buttons, over onto the side and construct this graphical user environment. Once you save your figure window, Guide will generate a MATLAB file with functions for each one of the features you've put into the box. So in here, in the MATLAB file, it'll generate a setup function to create this window and set everything in the way you organized it with the Guide toolbox. And then it'll also generate these actions for each one of the features you've added here. So I added 2 push buttons, A and B, and the Guide platform generated my MATLAB code and generated these push functions. Now when a user comes and runs this program, it'll start up with the initialization step here, run the setup, and the window will be generated. Now, when a user clicks on a button, button A or button B, the callback is executed, and the callback has this window execute these functions. And these 2 functions are called callback functions, and it's for the window to call back into the code and perform some sort of action. So for push button A, we would have a clear, maybe clear the plot window, and then maybe push button B would be an exit command to close the entire program. So since we're working in functions here, we have to be real careful with our variables. Any locally defined variables will disappear upon the exiting of the function. To get around this, MATLAB uses a handle object, and you can treat it as a struct just like we talked about before. And that's available generated by the Guide platform. So each one of these functions here will have a handle fed into it. And the handle is created up here in the setup window. So to save variables and pass between functions between the setup and when buttons are pushed, you just save the variable as handle.variable and you put it into that structure of the handle. And then this carries each variable to the subfunctions, either push A or push B. So now we'll see a demo of how to generate this window in Glide.
Okay, for our final demonstration today, we will talk about graphical user interfaces. And the best way to generate graphical user interfaces in MATLAB is to use the guide toolbox. So we'll just type guide into our command window. It'll pop up our quick start. We'll select just a standard example template, a graphical user interface with a drop-down box, an update button, and a plot. So we'll click OK. And the guide interface will generate. And here we can see here, we are able to click features in order to bring out to our graphical user interface. We can add a button, we can add sliders, radio boxes, we can have input text, all sorts of features to our graphical user interface. Right now I'll just leave everything in the default so we can see how it all works. And when you're ready, you can just click save, provide a name. I will call this window.figure, and I'll save that. And then once you've saved your figure, it'll show up on the left hand side of your current folder, and MATLAB will generate this window.m file. And the window.m file is the method in which you use to execute your graphical user interface. So I'll close these functions down so everybody can see what's in this file. So we have an initialization code right here for generating the window to begin with. And then we have an opening function, and the opening function is what runs right before your window's displayed to the user, so you can run your calculations and your setup in there. The next major buttons will be the callback buttons from your features inside the window. So right here we have a push button 1 callback, so when your button number 1 is pushed, this function gets called. We have a file menu callback, an open menu callback, and all of these are when you select the, let me run the thing here. When you select these menu options, these callbacks will operate. And so the open generates an open to select a file. And when we click update, it runs the update command. So let's look at the push button callback. So if we run this, when we see the push button right here, if we push this button, it's running, the window sends a callback back to this window.m file for this function. And so at first it selects the axes, it clears the axes, and then it selects the index value for the pop-up. And so the pop-up here, we can see it has 5 options there. And so right now we're just plotting a random 5 numbers. And so based on the number, the switch statement for each of the cases here, case line number 1 is rand5, which we see here. Line number 2 is the sign function. Click update, and now it plots this. So when we click update, it reads the index value off of this drop-down box and then runs this plot command. And we're not limited to 2 dimensions here. We can do 3-dimensional plots and all sorts of functions. So as you can see, these are the same MATLAB commands that we're all quite used to running, and the only difference is that now the functions are being called by callbacks from when you push the feature such as a button, or you do a drop-down box and select a different index of the drop-down box. And then the same exact process exists for all of these different callbacks right here. For the open menu, we have a UI for getting a file, and so it searches for .figure files and then runs the open command on them. You can print dialog for printing the graphical user interface, and all of these are nicely set up by MATLAB beforehand, and this is all generated by the guide. So if you wanted to run your own code in here, you can write your own function and then have the function execute when the window is opened in order to populate data values. And then later you can have the function run more sophisticated responses to user input. All the while, Guide and Windows are taking care of monitoring for those callback events, such as clicks or zooms or moving a slider bar. So that's the basics of generating a GUI in MATLAB. There's incredible documentation on MATLAB's site for Guide. We can just show that right here if we type Guide. And as you can see, ways to build MATLAB GUIs. There's excellent documentation here and examples of how to go through it with videos for later exploration.